Hello my beautiful students, so welcome back to KCET Masterstroke with a new series, with a new session. I guess in the previous videos whatever the concept was discussed you understood, and please don't forget to comment me if you are having any doubts in any session. We will definitely point out your doubts in the live session itself with a proper interaction. So today we are going to discuss about the D and F block elements. So without further delay, let's get started. So here we are going to discuss about the position in periodic table, electronic configuration, general properties, oxides and oxoanions, important compounds, lanthanoids, actinoids. That's it. First we will discuss about the position in periodic table. Okay, so elements of D and F block, why they are termed like that? Because the last electron enters into the D and F orbitals respectively. If you just look at the position for the D block element, it is group 3 to 12, and for F block element it is like 4f and 5f orbitals are there, like last electron enters over there, and here you can see the transition metals, they are majorly the D block element, and inner transition metals, they are F block elements. Okay, this D and F block element, if you just precisely see, they have different space, that they have separate panel at the bottom of the periodic table where they are situated. But D block element we can call 3 to 12, but F block element they have a different panel that is represented just below the periodic table. Okay, let's proceed further. Okay, so transition metals, they are having 4 series, 3D, 4D, 5D and 6D. 3D is scandium to zinc, 4D is yttrium to cadmium, 5D is lanthanum and hafnium to mercury. Okay, 6D series actinium to RF to CN, that is basically some radioactive elements. Okay, inner transition metals, if you see, that is basically the second series, and that is 4F cerium to lutetium, and 5F, that is thorium to lawrencium. Those are actinoids. Okay, proceed. So these are the overall common electronic configuration for 3D series. You can see 3D 1 to 10, 4s 1 and 2, scandium to zinc. Okay, next if you see 4D series, then it is definitely 4D 1 to 10, 5s 1 and 2, and it is from yttrium to cadmium, right? If you see for the 5D series, it is 5D 1 to 10, 6s 1 and 2, it is lanthanum to mercury, right? If you see 6D series, it is 6D 1 to 10, 7s 1 and 2, and it is basically incomplete series, you can tell. Okay, proceed further. This is the entire periodic table. Here you can see 3 to 12. This is the zone for the D block element, and here we are having the separate panel. This separate panel for the F orbitals. Okay, I guess it's clear to you. The position is clear to you. Let's proceed. Okay, before proceeding, just one more reminder I want to give it to you people, that the Deeksha Karnataka channel already has launched the ABHYAS, the most awaited KCET test series, from where we are getting outstanding results throughout the last few years. So yes, don't take more time to think. Please enroll yourself in that if you wanna get top 1000 rank in upcoming KCET examination. It will give you 35 mock tests, so that will come up with some exam hall like simulation. Okay, so you can treat yourself as an aspirant of KCET who is actually sitting inside the exam hall and giving the exam. Okay, so please give it a try and boost up your level in the preparation of KCET. And one more thing I wanted to tell, along with that, it is some premium experience that Deeksha Karnataka channel is providing. So KC30 batch has been launched. So this is basically is provided with 30 days live online crash course. So basically ABHYAS KCET is a wonderful thing. Definitely it will give you the mock test, you can practice yourself. Okay, but sometimes for some student, some structured plan how actually you should proceed, from where you should study, okay, that particular mindset, that particular thinking needs to be grown. Okay, so KC30 will give you that particular structured plan, where it will give you the live online session by the expert faculties and previous year questions with solution. Every day there will be live doubt solving session, complete syllabus revision of PU1 and PU2. Okay, and chapter wise PYQ test format you will get, and mock test, 10 more mock tests as an additional, you can tell. And as you can see, the price that's going as of now, it's 2499. It will go up to 25th Feb, but later on it may increase. So yes, don't think that much. Take it, it's for your benefits to get top 1000 rank in upcoming KCET examination. So yes, take this series and boost up your rank. So yes, without further delay, let's proceed. Here we are going to discuss definitely a little bit more about the position. The transition element, they are defined as the d orbital element, d block elements only, who are incompletely filled. Okay, like I can just tell the example of zinc, or zinc. Let's take, if you take zinc in ground state zinc is having D10 configuration, right? So as a result of this, there will be no chance of transition. Transition when it is possible, when it is incomplete, means when there is a place for moving, right? But here is no place for moving, it's already it is filled, it's compact. Like zinc, cadmium, mercury, they are completely filled d orbital, they are not considered as transition element. Okay, so you have to check for those metals who are having incompletely filled d orbital in their ground state itself. Okay, and if you see in the common oxidation state also, okay, like if you just discuss about the Cu, copper, so copper plus Cu plus, that is also 3d10 configuration, it is also will not behave as a transition element. Okay, so this is thing, so they are called as pseudo transition elements in that regard. Okay, I guess it's clear. Sometimes in the PU level the question comes, why zinc is not considered as a transition element? I guess you can answer no. Next, this is the electronic configuration that is given out there, you can just have a look onto it. Okay, chromium, manganese, these are very important, just have a look into it. I guess it's clear to you. Let's proceed further. This is the 4th series. Okay, one question, which element is not a D block element? Okay, platinum, lead, ruthenium, osmium. So lead is a P block element. Okay, let's proceed. Okay, one more thing, that just an additional support that Deeksha Karnataka channel is providing to you. Just below my video in the description, you will see one mock test link over here. It's a KCET free mock test. Yes, it's completely free for you people that we are providing. Okay, so please make sure that you are going to the link. Okay, and once you will just tap the link, this particular phase will be opened up. Here you just put your mobile number, you will get an OTP, please put that and you will get a free mock test for you. Okay, like that. Okay, so please make sure you are attending that mock test so that you understand where you are exactly belonging in accordance to your preparation. So don't miss out this chance. Please grab the opportunity. Okay, so yes, let's proceed further. So now we are going to discuss about the trends in physical properties. We are going to discuss physical properties, enthalpy of atomization, atomic and ionic radii, ionization enthalpy, oxidation state, trends in M2 plus to M reduction potential, trends in M3 plus to M2 plus, and trends in higher oxidation state, magnetic properties, colored compounds, complex compounds, catalytic properties, and interstitial compound, finally the alloy formation. So these 14 things we are going to learn one by one. Okay, So let's proceed one by one. Okay, first we are going to discuss about the metallic properties. So definitely they are highly tensile strength, ductility is there, malleability is there, high thermal and electrical conductivity you can observe, and definitely metallic luster you can observe out of it, very hard in nature, high melting point, high boiling point. And why? Because it is forming a very strong metallic bonding. Okay, the stable electronic configuration of manganese and technetium means that the electrons are less delocalized, so they can't move freely in the electron C to the contribute to a metallic bond. Okay, this is for the manganese and technetium 2 cases, but rest of the cases you can see strong metallic bond. Okay, let's proceed further. Okay, so here we are going to discuss the few things, that is melting point, boiling point we are going to discuss. Okay, so this is basically what is ultimate valence shell. Next to the valence shell we call it penultimate shell. Next we can call it anti-penultimate shell. Okay, so here you can see the electronic configurations are also given here, and this is the overall trend of the melting point versus atomic weight. Okay, so sometimes they ask the question with respect to like 3D series, what is the element which is having the strong maximum boiling point, maximum melting point, so that your answer will be chromium, and least melting point, that is your manganese. Okay, just now we discussed the reason. Okay, because it cannot contribute in the electron C model. You can see the last thing. Okay, they can't move freely in the electron C, right? That's the reason metallic bond is not that much strong. As a result of this, melting point is very low for manganese and technetium. And now another thing, in D block element, which one will show you the maximum melting point, that is of tungsten. Okay, so remember this tungsten. For this 3D series, remember chromium and manganese technetium. These two phenomena also you have to remember. I guess it's clear. Let's proceed. Okay, which element has highest melting point? As I told you, this is tungsten. Okay, next. Okay, enthalpy of atomization. So what is enthalpy of atomization? This is basically, if you are having a metallic bond, then to break the bond, to separate them into the individual atom, the energy you require, that is called the enthalpy of the atomization. So along the period it increases, down the group it decreases. Okay, so it doesn't happen in case of manganese, the reason I already told you. Okay, I guess it's clear. This is the trend out of it. Let's proceed. Atomic radius and density, if you see, it basically depends upon the screening effect. Okay, it actually gets affected by the nuclear charge, effective nuclear charge. So what basically happens, let me tell you, my dear. So see, if I am having so many electrons in front of me, let's say I am the nucleus, if I am having so many electrons in front of me, so I can't see who is outermost, right? But if I understand there are so many electrons, but they are diffused, here one, there one, here one, there one, like that, they're sitting diffused, right? In that case I can see the outermost electron. So the same thing happens in case of D and F electrons as well. So what basically happens, D and F, D means 10 electron, F means 14 electron. Can you imagine the amount of inter-electronic repulsion that gets triggered when the electron gets filled up in D and F orbital? So a huge number of inter-electronic repulsion makes the electron diffused, delocalized. As a result of this, nucleus becomes open to the outermost orbital, outermost electron. As a result of this, as more and more D and F orbital keeps coming, then the effective nuclear charge, means in the center also, inside the nucleus, number of proton also increases. As a result of this, with a full effective nuclear charge, it pulls the outermost electron towards itself, and as a result of this, atomic and ionic radii decreases, right? So what is happening? I understand D and F orbitals are so big, so many electrons are there, but the radius, the way it should increase, it is not increasing. Why? Because of the screening effect. The D and F orbitals electrons, they are poor screener, poor shielder. They can't shield the nucleus. What's the reason behind it? The reason is they are having inter-electronic repulsion. Inter-electronic repulsion predominates, right? So nucleus becomes open to the valence shell. So it pulls the valence shell electron. As a result of this, overall radius decreases. So this is the phenomenon that happens over here. Okay, so along the period, here you can see first scandium, titanium, vanadium, it increases. So here in this case, effective nuclear charge is greater than screening effect. Okay, screening effect means not that much d electron, only 4 to 5, right? But later on, whenever iron, cobalt, nickel, there the electron gets entered, then they becomes equal. Effective nuclear charge and screening effect becomes equal. But after that, after nickel, whenever d orbital gets filled up, D10 configuration, then effective nuclear charge becomes lesser than that of the screening effect, and hence zinc becomes more, copper becomes more. Okay, I guess it's clear. Yeah, let's proceed. This is the overall trend. Okay, atomic radius down the group, here you can see after scandium, yttrium and lanthanum, but here they becomes almost equal. This is the consequence of the lanthanide contraction. So what is lanthanide contraction? So after the lanthanum, the atomic radius, the way it should increase, it doesn't increase because of the poor shielding of D and F orbitals. Okay, that is basically the lanthanide contraction. After zirconium, hafnium atomic radius should increase, but it doesn't increase, it is similar. They are called as chemical twins, okay, because of the lanthanide contraction. Okay, so I guess it's clear. Okay, let's proceed. This is the lanthanum, hafnium. Okay, so here you can see ionization enthalpy. So there is an increase of ionization enthalpy along each series of the transition element from left to right, okay, due to the increase in internuclear charge, right? Because D and F poor shielding, so internuclear charge will increase, right? So the trend of steady increase in the second and third ionization enthalpy breaks for the formation of M2 plus and Fe3 plus ion respectively. Okay, so as you can see, ionization enthalpy of Mn2 plus is less than that of chromium plus. That's obvious, but whenever it comes to the Fe2 plus becomes lesser than that of the Mn2 plus. Okay, so I guess it's clear to you. Let's proceed. Oxidation state. Okay, so we can see variable oxidation state, right? Why? Because of the participation of the d electrons. Okay, so ns and n-1 d orbital, they takes part. As a result of this, a variety of oxidation state we see, except scandium and zinc. Scandium and zinc, why no? Because scandium is only 4d1, right? Sorry, 3d1, right? So 3d1 if you replace and 4s2 if you replace, then it will have scandium 3 plus, it will get the noble gas like configuration, so it will prefer to be 3 plus only. Now in case of zinc, if you see, if the 4s2 electron is released, it is d10, 3d10, right? It is stable configuration. So for scandium and zinc there is no change, but in case of manganese, if you see, up to +7 oxidation state, right? So many oxidation state you can see because of the d orbital electrons. Okay, so manganese is highest in order to show the variation. Okay, let's proceed. Along the period, okay, M2 plus to M reduction potential, along the period it becomes less negative. If M to M2 plus is easy, then E0 value will be more negative. Means we have to check the electronic configuration, then we can tell that if M to M2 plus becomes easy, like for zinc, Zn2 plus is very easy, right? Then E0 value will come towards the negative zone. Okay, next, here comes the value. You can see just the value for the reference it's given. Let's proceed. Here you can see for the manganese and nickel also they pointed it out. Okay, so now here you can see few examples are given. Why? From scandium 3 plus to scandium 2 plus. Why it will come from scandium 3 plus to scandium 2 plus. Scandium 3 plus is very much stable. It is having the noble gas-like configuration. That's the reason low value. The value is low because scandium 3 plus is very stable. So it will not come to scandium 2 plus easily. Right? Now if you just proceed with this example, Zn3 plus to Zn2 plus, it will nicely come. Okay, high value you will see because Zn2 plus is very stable, D10 configuration, right? That's why high value. You have to check where it is coming or from where it is coming, in which particular species it is coming, from where it is coming. Like this case, it is coming to Sc2 plus, that is D1 system, right? So compared to that, if I stay in D0, means P6 configuration, that is more stable, right? Then why it will come to Sc2 plus, right? That is the stability of Sc3 plus is more, that's the reason low value. But here Zn2 plus, it will come nicely, that's why high value. Okay, here Mn2 plus, it is coming to Mn2 plus, very stable oxidation state, right? That's the reason Mn3 plus to 2 plus it is coming. Mn2 plus is very stable, that's why high value. Next example you can see Fe3 plus to Fe2 plus, again low value you will see because Fe3 plus is more stable than that of the Fe2 plus. That's the reason as stability of Fe3 plus is more, you will see the low value in the reduction potential. I guess it's clear to you. Let's proceed. Okay, stability of the higher oxidation state here we will discuss. Okay, so first we will discuss about the fluorine. So fluorine to some extent it stabilizes the higher oxidation state whenever it is bonded with some cobalt compound, like you can see COF3, okay, because of the lattice enthalpy. Okay, another case you can see VF5 type of compound, okay, CRF6 type of compound, okay, this is because of the higher bond enthalpy. Okay, now fluorides are unstable in low oxidation states. Okay, like you can just take the example of VX2. Here X should be taken as chlorine and bromine and iodine. Means with vanadium, the if you take chlorine, bromine and iodine, then lower oxidation state you should take, but in order to make the higher oxidation state complex compound for the vanadium, then you have to take fluorine only, okay, or else you have to take some other halogens. For copper itself, copper also you can see you have to take chlorine, bromine and iodine only because it is stabilized in low oxidation state only. Okay, next. One more thing, one question it comes like that, CuX2 are known except CuI2. Why? Means CuI2 it doesn't exist. Why? Because what copper 2 plus does, it oxidizes I minus. It oxidizes I minus to I2. Then if it oxidizes I minus, if it forms I2, then how does this CuI2 compound will form? There is no chance, right? So yes, let's proceed. Copper 1 compounds are unstable in aqueous solution and undergoes disproportionation reaction. So copper plus 1 it disproportionate to give you copper 2 plus and copper 0 oxidation state. Okay, the stability of copper 2 plus rather than copper plus is due to the much more negative enthalpy of hydration. Okay, negative enthalpy of hydration makes the copper 2 plus ion more stable in the aqueous solution. Okay, so few questions on here. First, why CuI2 does not exist? Next, this disproportionation of copper 1. Next, why this copper 2 plus is stable in the aqueous solution. I guess it's clear. Let's proceed further. Okay, so here we will discuss about the like oxygen can form multiple bonds. This particular capability is there. That's the reason manganese can form bond with oxygen in higher oxidation state. Okay, so definitely oxygen has the capability to stabilize higher oxidation state even better than that of fluorine. Okay, so we know highest oxidation state is observed by manganese, that is +7 oxidation state. But if you take fluorine, it can form up to +4. means manganese MnF4 compound. But whenever it comes to the matter of oxygen, manganese can form +7 oxidation state with oxygen. Okay, so that's Mn2O7 we know. Okay, so because of these things, okay, like metal always takes oxygen as a priority to make the bond or to stabilize their higher oxidation states. Okay, let's proceed further. Here we will discuss about the magnetic property. It's a very common thing that we study, that paramagnetic, diamagnetic and ferromagnetic. Paramagnetic means it's feebly attracted by the presence of magnetic field. Now diamagnetics, they are strongly attracted. Ferromagnetic means they repel. Okay, they repel the magnetic field. Next, magnetic moment we can calculate in if we are having the unpaired electron present over here, that is under root n into n plus 2. Okay. Next, color. The main property that we observe for the transition element is the color, different color. So what happens basically, whenever it is in the case of transition metal, we are having D to D transition. Okay, so in crystal field, whenever we will discuss in the coordination chemistry, you must have learnt it. Crystal field, d orbital gets splitted in T2g and Eg orbital, right? As a result of this, whenever the electron they gets transferred from the lower energy state to higher energy state, then this excitation, it corresponds to the frequency of the light that is absorbed. Okay, so this particular frequency, it lies within the visible region, and as a result of this, with respect to the frequency, we see specific colors of the compound. Okay, definitely complementary color we observe. Okay, whatever the frequency is absorbed, complementary color we see, we can visualize, right? So I guess you understood. So whenever it comes to the matter of the color of the compound, your answer should be D to D transition. Okay, I guess it's clear. You can see mercury iodide, chromium oxide, there are several compounds, they have beautiful colors over here. Okay, let's proceed further. Formation of the complex compounds. Okay, so complex compounds are those in which metals they gets approached by the ligand, an electronegative species, okay, or electron rich species. Okay, so ligand approaches to the metal center, right, and multiple ligand can approach, and they can form the complex. A few complexes examples are given here. Why they form the complex? First, smaller size of the metal ions, okay, and high ionic charge, okay, and availability of the d orbital, vacant d orbital, that is the most important reason to form the complex. I guess it's all good. Let's proceed. Catalytic properties, why they work as a nice, catalyst in different reaction. So why? Because of the multiple oxidation state and ability to form complex. This is the main reason why they show catalytic properties. One example, vanadium oxide can be used in the contact process. Ziegler-Natta catalysts are there. Nickel, finely divided nickel or iron, they can be used. Nickel is used for the hydrogenation, or iron can be used in the Haber's process. Okay, this type of thing this is how they can be used as a catalyst. This reason you remember. Okay, proceed. Interstitial compounds is a very important thing. Okay, interstitial compounds are formed whenever a small atoms such as carbon, nitrogen, hydrogen, they get trapped within the crystal lattice. Okay, and they are non-stoichiometric. Okay, and they can't form any kind of neither covalent nor ionic type of bond. Okay, so one example you can see, Mn4n. Okay, VH 0.56, this type of thing. These are called interstitial compounds. So these are having sometimes a very high benefits it gives to the industry, okay, because high melting point, it shows high melting point than that of the usual metal, okay. They becomes very hard, metallic conductivity enhances, okay, chemical inertness enhances, okay. I guess you understood this is the interstitial compounds. The definition and examples are very important. Alloy formation, why? Because of the similar ionic radius, okay, and yeah, some other characteristics as well, okay, like we can take the example of brush, right? Copper and zinc, quite similar characteristics, very close to each other, atomic and ionic radii also very close to each other, okay. So the alloy, actually what is the benefits? They form very hard, overall compound becomes very hard, and the high melting point, okay, it helps, it gives some benefits in the industry, okay. So yeah, brass, bronze, you can just give the example. Next, oxides and oxoanions. Here you can see, so few basic thing you have to take, you have to just remember this is the entire NCERT, that particular portion is taken, only the highlighted portion you have to remember, okay, that is here, okay. So here you can see transition metal, like they can form oxide definitely, and we need high temperature for that, okay. Scandium, if you look for the scandium, it forms oxide. This is very ionic in nature, okay, and oxidation number of a metal, it increases, ionic character decreases, hence melting point also decreases. This is in accordance to the Fazan's rule, okay. One example you can see, if you discuss about CrO3 and V2O5, then V2O5 is having low melting point, okay. With respect to that, the question may come. So now if you just discuss about the oxides of the manganese, MnO, Mn2O3, MnO2, Mn2O7, if you see the oxidation state of manganese is increasing, right? Hence ionic character increasing, sorry, ionic character decreases, right? So as a result of this, you can tell that melting point becomes lower, okay. Basically Mn2O7, if you see, it is green colored oily liquid in liquid temperature, okay. So with the higher oxidation state, the melting point actually decreases, okay. So that is the marked portion is here, you can see, okay. Let's proceed further. Few important compound we will discuss, K2Cl2O7 and MnO4. Preparation, structure and chemical reaction is very important. So first we will proceed with the preparation of potassium dichromate. So potassium dichromate, we will start from the FeCl2O4 chromate ore that is treated with sodium carbonate, then in presence of oxygen, then it forms sodium chromate. Then sodium chromate is acidified, it forms sodium dichromate. Then sodium dichromate is treated with KCl and it forms K2Cl2O7. Okay, this is the preparation. So this is how it looks like. This is the chromate ion, this is the dichromate ion. So here one more thing, chemical property, you can see chromate and dichromate, it actually matters just a presence of H plus and OH minus, okay. So if you decrease the pH, means if you increase the concentration of H plus, then it will form dichromate. Again in dichromate solution, you increase the pH and decrease the concentration, it will come back to the chromate. The color will be changed, okay. Let's proceed. Oxidizing agent, dichromate is a very strong oxidizing agent. It oxidizes I minus to I2, okay, in acidic medium. It oxidizes H2S to sulfur, okay. Next, it oxidizes SN2 plus to SN4 plus. It's a very strong oxidizing agent, okay. It oxidizes Fe2 plus to Fe3 plus. It's a very common reaction. Next, okay, next we will proceed with the potassium permanganate preparation. So here you can see by fusion with MnO2. So MnO2 can be fused with KOH in presence of oxygen to give you K2MnO4. Further, this K2MnO4 in presence of acid, it will give you MnO4 minus and MnO2, okay. Next, commercial method of preparation. Here you can see MnO2 that is fused with KOH oxidized with air or KNO3, it will give you the manganate ion. Manganate ion further on electrolytic oxidation, it will give you MnO4 minus. Okay, same thing only, the reaction here, this is a reaction by fusion with MnO2 and this is fused with KOH, that's it. Okay, let's proceed. Okay, one more commercial method here you can see Mn2 plus in presence of S2O8 2 minus, it can also form MnO4 minus. Okay, let's proceed further. This is the structure, tetrahedral compound, like this is manganate. Okay, tetrahedral manganate ion, that is green. It is tetrahedral permanganate ion, that is purple. Okay, this is manganate, this is permanganate. Okay, let's proceed. Chemical property, it's a very strong oxidizing agent. It's a dark purple color, almost it looks like black. Okay, it is isostructural with KClO4, it's a very important point. Okay, and its intense color is definitely due to charge transfer phenomena, metal to ligand. Okay, so it involves magnetism but very weak temperature dependent magnetism. Okay, thermal decomposition if you do, it's very important actually. KMnO4, if you heat this, you will end up with K2MnO4 and MnO2, one gas, that is oxygen. It's a very important question that comes out. Okay, let's proceed with the chemical properties. Few reaction you can see. MnO4 minus in acidic media, it forms it can exchange 5 electron. Okay, very high acidic if you keep, very high acidic media if you keep, it actually can form Mn2 plus, +7 to +2 oxidation state. If you keep it neutral, then MnO4 minus can be converted to MnO2. If you keep it basic, then it can form MnO4 2 minus. Okay, let's proceed. It's a very strong oxidizing agent. As you can see, in acidic media, it can transfer I minus to I2 gas. Okay, it can convert NO2 minus to NO3 oxidizing. Okay, SO3 minus to SO4 2 minus. Okay, let's proceed. Few more examples are there. From S2 minus it can convert to sulfur, Fe2 plus to Fe3 plus, and it's very important as a question it comes basically. If you put oxalate in highly acidic medium with KMnO4, then it will convert it to carbon dioxide, CO2. Okay, let's proceed. In neutral media, what it does, the reaction with iodine, it's something very important to remember. In neutral media, it changes I minus to IO3 minus. In acidic media, it was something I minus to I2. Here, I minus to IO3 minus. Okay, S2O3 2 minus to SO4 2 minus, Mn2 plus, Mn2 plus to MnO2. Okay, so few more, most important thing that you have to remember, the change in iodine. Okay, change in nitrate, change in oxalate. Okay, these are the most important. Next one question you can see, KMnO4 acts as an oxidizing agent in alkaline media. When alkaline KMnO4 is treated with Ki means I minus. Okay, so iodized ion is oxidized to IO3 minus. Neutral and alkaline, they are similar. Okay, IO3 minus they will convert. If the same question would have come in the form of acidic media, then you could tell that it is I2. Okay. Okay, so this is the position of lanthanides. We are going to start. Here you can see this is the lanthanide series, this is actinide series. Okay, so lanthanide, as you can see, the last electron enters into the 4F, and these are called the rare earths element. Okay, this is the general electronic configuration. Xenon, after that 4F 1 to 14. Okay, then D 5D 0 to 1. Okay, 6S 2. That's it. Let's proceed. This is the entire lanthanide series along with their electronic configuration. You will get it in your NCERT as well. Let's proceed. Atomic size, definitely there are decrease, steady decrease because of the lanthanide contraction that already I explained. Okay, why? Because of the pore shielding of the 4F and D orbitals. Okay, Let's proceed. Here comes some consequences of lanthanide contraction. The first is similar size, zirconium, hafnium, I guess you remember. Okay, so because of the similar size, they become very much similar in their chemical and physical properties as well, that they become very much difficult to separate from their ores itself. Okay, basic character decreases from LaOH whole thrice to LuOH whole thrice. Okay, basic character decreases. Okay, 4D and 5D radius become similar, like one example zirconium, hafnium, niobium, tantalum, molybdenum, tungsten, they are of quite similar radii. Okay, let's proceed. Common oxidation state is +3, but +4 and +2 are also observed. These are the elements. Proceed. Color is also there here. FF transition, okay, and it depends upon definitely how many electrons are there within it. Okay, so definitely 4F0 and 4F14 elements are colorless because they are fully filled, and this is 0, no electron. Okay, next here comes the magnetic properties. Lanthanum and lutetium, they are diamagnetic. Cerium and erbium, they are diamagnetic. All Ln3 plus are paramagnetic, and these are the information that you should remember. That's it. Okay, Nd, that is neodymium, that is most paramagnetic in nature. Few information you can remember them. Next, few reaction with whenever it is heated with sulfur, nitrogen, carbon. Okay, so sulfur you can see, nitride you can see, carbide you can see, hydroxide, halogens. A reaction with acid will liberate the hydrogen gas. Okay, this type of reactions are given. Okay, very important thing, 2 marker question can come in your board examination, as well as a PYQ can also come. Sorry, PYQ, how it will come, I mean to say in the KCET, the question also can come out of it. What is mismatch? Okay, so mismatch is basically like lanthanum, that is 95%. Okay, only in this particular composition, whenever there are stresses of different p block elements such as calcium is S block, aluminium, carbon, sulfur, if they are having some stress of this other element, traces of this other element, then they are called the mismetal. Like lanthanum 95%, iron 5% with the traces of sulfur, carbon, calcium and aluminium, they are called mismetal. Okay, let's proceed. This is the actinoids, I guess this is the position you remembered. This is the general configuration, and they are very much radioactive in nature. Okay, these are the all actinoids with their electronic configuration. You will get it in your NCERT. Actinoid contraction is also observed definitely because of the F orbitals, and common oxidation state is +3, but +7 and +6 also observed. Next, yeah, that's it that we are going to discuss about the D and F orbital. Later on, definitely we will come up with the PYQs, and if you are having any doubt in any portion, please don't forget to comment me below. And if you have not subscribed, please subscribe our channel, and don't forget to like and share as well. Thank you for watching the video.